Occur a number of times throughout the week. And the sort of basic idea behind this tool is, what if we had a sequence of queries issued against a database, and we only needed to know the answers to the queries whose answers fall above some certain threshold or within some certain range. And one way, if we had a tool like this, that we might apply it, is maybe we could then cheaply check, in some sense, whether, when a new query comes in, whether we already have a good sense of what the answer should be. And if that's the case, maybe we can somehow avoid paying in full for that query. And if we don't have a good sense of what the answer to that query should be, we're going to have to pay for it in some sense on the data. So at a very high level, that's the sort of intuition for the type of tool that we're trying to build. But think of it just as, for now, we'd like to just handle queries whose answers fall above a certain threshold. And I mean, this sounds a lot like things that we've been talking about so far. So this may remind you of the report noisy max. I mean, there we were just looking to report the max, and then we realized, okay, that's in some sense an instantiation of this exponential mechanism that we saw earlier today. But what's different here is I'd like us to be able to handle an adaptive sequence of queries. So we don't know the entire sequence in advance. We can't, so there's no sort of obvious way to apply the exponential mechanism, but we'd like to, despite not knowing that sequence in advance and it potentially being adaptive, we'd like to somehow be able to get the same types of guarantees in terms of a privacy accuracy trade-off as we could have gotten using the tool of the exponential mechanism. So that's the idea here. So the theme of adaptivity is continuing from Kobe's talk, and the toolkit that he provided us will also be relevant here. So let's start with sort of a simpler version of the problem and a simpler version of the algorithm. This is really going to be the key mathematical component, and then we'll just sort of apply things that we already know on top of this. So the simpler problem is this. So we're given an adaptive sequence of queries and some particular threshold. And as each query comes in, if the answer to that query is approximately below our threshold of interest, we just say below. We don't tell you an approximate answer for the query beyond that. Just say below. And if we finally get to a query that falls approximately above our threshold of interest, we say above, and then we quit. We answer no more queries. This is the thing we'd like to design. So here's the algorithm that we're going to be working with, and it's probably pretty much what you would have guessed, except maybe you would have done this sort of randomization in slightly different points, or re-randomize at slightly different points, and there's a bit of subtlety in the choices that are being made here, which will come out to some extent when we work on the proofs here. But the basic idea is we have as input a private database and some adaptively chosen stream of low sensitivity queries or sensitivity 1 queries, and some threshold of interest. And we're going to produce a stream of responses. So as each query comes in, we need to respond to it. And the way we're going to do this is, first we're going to take that threshold of interest, and we're basically going to say, okay, let's add some noise to that threshold to get some new version of the threshold. And then the next thing we're going to do is, as the queries come in, we're going to evaluate them, but then instead of checking whether the evaluation of the query falls above our noisy threshold, we'll check whether the evaluation plus some noise falls above the noisy threshold. If evaluation plus some noise falls above the noisy threshold, we say above, and then we halt. And if it falls below, we say below, and we continue to the next query. So it's a very, very simple algorithm. The subtleties, like I said, are just in sort of where we place the noise and when we remove the noise. So this choice of the noisy threshold is sort of once and for all, but this choice of the noise to add to the value of a query is fresh for each of the queries. Okay? And so what we'd like to do is analyze this algorithm to see that this is actually going to give us these types of guarantees that we wanted. So questions about what's happening in terms of the algorithm as it's stated, or what we're trying to achieve. Okay, great. So the claim that we'll start with is the claim that this above threshold algorithm is epsilon differentially private. And so basically it's going to start as you expect it to. So we're going to consider x and x prime, say neighbors, neighboring databases. And again, sort of the usual thing. We'll go swimming. We will fix any output. And what's the form that an output's going to take from this algorithm? Well, it's an algorithm that gets queries one at a time, and it says below, 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 until it gets something that's above, and it says above, and then it stops. So what are the possible outputs? There are vectors of belows for some number of belows, and then finally an above. So we're going to write this, fix any output of the form, below, up to below, for some, say, L-1 belows, and then finally an above. And say this L is less than or equal to K for some K. And so now here is like one of the sort of more subtle points of what's going on here. So in what follows, sort of the right way to think about it, perhaps, is that we're taking an expectation over a whole bunch of things. We're going to be taking an expectation in the following calculation over the choices of noise that we add to each of those true evaluations when we're checking whether or not they're above the noisy threshold. So those are those noise additions. And we're going to be, so we've got the first L-1 of those. And we're also going to be taking an expectation over the choices of the functions. And there's a bit of subtlety here in the sense that this is an adaptively chosen sequence of functions, but fixing the news up through L-1 and fixing the functions F1 through F sub L-1, for example, that determines what F sub L should be. And so now, in order to sort of simplify how we're going to write things, what I'm going to write instead is to say, fix a choice of the news and the Fs. And we're going to do an analysis in terms of a fixed setting of these possibilities. And then what we're going to be doing is considering randomness of the t hat and nu sub L. And I need some more room here. So for notation here, it's going to be useful for us to have the concept of sort of the largest noisy answer so far. So that's going to be the max over everything up until right before L of, these are F's, not Q's, F sub j of x plus nu sub j. Okay? And so what we'd like to do is we'd like to understand the relationship between the probability over the choice of this noisy thresholds and the choice of the noise that we add to that Lth answer that our algorithm above thresholds, given a database and a sequence of queries, and T epsilon, returns some A. So let's say this is A, that particular output of interest. Okay? And so what is this? Well, this is just, we want to understand the relationship between this probability and the probability that given the neighboring database X prime, we see A. So let's look at this first probability and understand what's going on here. So this is the probability that noisy threshold falls above Rx, and it also falls below F sub L of X plus nu L. So basically what I'm saying here is the probability that we return a sequence with L minus 1 belows followed by an above is equal to the chance that we've chosen a threshold such that that threshold falls above all of the noisy answers that we've seen so far, but below the noisy answers that we see today. Okay? And so just to rewrite this, so probability that I fall in this range. And what we'd like to claim is basically that this is at most e to the epsilon times that probability that AT on X prime, blah, 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 returns A. And if we could get that relationship, then we'd be done. So that's what we're going to be working on here. Okay. So let's sort of continue on here. So we're going to write this as the integrals over some V and some T is the probability that our noise that we add to our current round's answer is V. The probability that our noisy threshold is T times, and if you haven't seen this notation before, I just mean I'd like to put weight 1 on the cases where this condition holds and 0 otherwise. Actually, this is not going to fit. Let me make it fit. Going back here. So times so now here comes the part of this proof that I don't like. And the reason I don't like it is because I don't have a really elegant way to explain the intuition for what's about to happen here. So I'm going to do my best. So what I'd like in some sense to claim is that the way this proof works is it says, hey, look, if there's some setting of randomness that induces a particular behavior of this algorithm given database X, there's some closely related setting of the randomness that induces the same behavior on a neighboring database X prime. That's what I wish the intuition were. It feels like almost the right intuition. It's not quite how the proof feels like it goes. So the way that I'm going to do this proof here is I'm going to do a change of variables here. And the change of variables is sort of intended to capture an alternative version of this threshold and of this noise that would be the threshold and the noise that you needed under X prime. So I'm going to define this V bar to be our regular old V plus Rx minus Rx prime plus F of, so this final function of X prime minus F of X. And I'm going to define this sort of alternative T, this alternative noisy thresholds to be the regular t plus rx minus rx prime. Okay? Now, these kind of look like they're a little bit out of nowhere. As we proceed, you'll see a bit why these are the right sort of substitute versions of the noise and of the noisy thresholds. But this is the thing I really don't love about this proof, is I don't have a really crisp intuition for how to explain what's going on here. But the intuition that I wish were right is the one that I've given to you. So let's notice something here. That, well, what can we say about v bar minus v? Some bound on how big this could be. Well, okay, let's do an easier one, actually, maybe. So let's start with t bar minus t. What can I say as a bound on how big that could be? So this is the point where this is kind of difficult to sort of see everything at once. But all you need for right now is the V's and the T's, and you need to remember what the R's were. So remember, the R is this maximum noisy value that I've seen so far. So we have an R of x, which is the maximum noisy value that I've seen under database x, and we have an Rx prime, which is the maximum noisy value I've seen under x prime. And this is maximum up through L minus 1, and we've fixed these functions and we've fixed these news up through L minus 1. So really the only thing that's changing when I look at R of x prime versus R of x is the database, okay? And so when I compare t versus t bar, how big can that difference be? You said 1. Pardon? Yeah, exactly. So the maximum sensitivity, and I said these were going to be sensitivity 1 functions. So great. Okay, so the trickier one is how far apart can the v and the v bar be? So each of the f's, we just said, is 1 sensitive. So we could get a difference of 1 from over here, right? And we just noticed, well, the R's can give us a difference of at most 1. So we're getting a difference of at most 2, right? Make sense? Okay. So we've got these sort of substitute V and substitute T that we're going to use in this proof. And a little bit later, it'll be useful to us that they're not so far off from the originals. Okay, so take this as an aside. And let's continue from where we were. So now we've got this integral and probability that are new. Now I'm going to do the substitution of my v bar for my v and my t bar for my t. So probability that my noisy threshold is now t bar times this 1 of, so t, well, let me not write it as t. Let me write it as t plus r of x minus r of x prime, because that's my substitution, is in the range r of x, comma, and this gets a little bit annoying. Here we go. F of x plus v plus r of x minus r of x prime plus f of x prime minus f of x. All right, did I do that substitution right? So my v became a v bar, which is a v plus r of x minus r of x prime plus f of x prime minus f of x. Somebody should check me that I did this substitution right. Did I get something backwards?
It's t minus or plus or?
So t should be t plus r of x minus r of x prime. So I could have written t bar here, but I'm writing it out in terms of t. So I substituted each of my t's with a t bar and each of my v's with a v bar in here. And then I'm being very explicit about this particular instantiation of the t bar. Yeah, like I said, this. Here, let me add some more space. Sorry, say again. So this should be t plus something. So sorry, this is a t bar here, and this is a t.
Why not t bar? I mean, you want to change the value of t bar.
So this is equal to t bar, and I just substituted back in for convenience. So perhaps I did too many steps at once. So this is a t bar, and this whole big annoying thing is a v bar. Yeah? Makes sense now? Okay. So now that I have this, now I have something that I can work with a little bit. So first let's notice that I've got a little bit of easy stuff to do. So let's get rid of this and get rid of that. So I've got now integrals, probability that my new is v bar, probability that my noisy threshold is t bar, times indicator. So now I'm going to subtract from both sides here. So from sort of this side and from these two pieces, the ends of here, I'm going to subtract this r of x minus r of x prime, okay? And so now I'm going to say this is the indicator that t is in the range between r of x prime and f of x prime plus v. Right? And now what I'd like to do is I'd like to say something about the relationship between the probabilities here and the probability that my noise was v. What can I put here? So in order to answer this, you kind of need to go back to the algorithm to remember what our noise draws looked like. So these news were drawn as Laplace 4 over epsilon, and then we have this bound here of 2. So what can I say here? So I've got sort of a Laplace draw, Laplace 4 over epsilon, and I want to understand what's the relationship between the probability that it takes on a particular value versus the probability that it takes on a value that's at most 2 away. So e to the epsilon over 2, right? I mean, so I want to upper bound this. So wait, I don't know which way it goes. I don't know if it got bigger or smaller. We just know these absolute values. So I want an upper bound. So I'm going to do an e to the epsilon over 2. Okay. And now I want to do the same sort of analysis here on the second probability. So I'm going to have something times the probability that my t hat, my noisy threshold, is t. The question is, what do I put here? So let's go back to our algorithm and remember what we chose here. So these were Laplace of 2 over epsilons right here. And now we have to remember, okay, how different can t and t bar be from each other? Can be at most 1. And so what can I fill in here? e to the same, epsilon over 2. Okay, great. You have a sense of where this is going, I suspect. Okay, and so now we've got this times indicator of t falling in the range between r of x prime and f sub L of x prime plus v dt. Okay, so we've got this e to the epsilon times, well, let's go back. Pardon, say again?
This is what's needed to prove epsilon differential.
Sorry, I missed one word of what you said. This is what's needed in order to... Exactly. Yeah. So now that we've gotten back to the point where we're going to talk about probabilities, this is the probability that my t hat is exactly what I wanted. So my t hat is such that it's bigger than all of the noisy measurements I've taken so far under x prime, and simultaneously, my t hat triggers me to say above, given our x prime. So what do I need for that? Just this. Okay, so are we done? Pardon? Yeah, so would anything be different if I swapped my x and my x prime? Was there anything asymmetric that happened here in this proof? So it was a long proof. So let's sort of go back and see, was there anything asymmetric going on here? X and x prime neighbors? Nothing asymmetric so far, but we should check ourselves here. Anything asymmetric here? Any assumption about which was the bigger one? Nothing so far. When we were talking about our v bar versus v and our t bar versus t, we didn't do anything asymmetric. When we did these bounds on the differences, there was nothing asymmetric. We didn't assume that one resulted in larger or smaller values, right? Nothing asymmetric, nothing asymmetric, nothing asymmetric. I think we're good to go. Okay? All right, so we have a somewhat long proof that this above threshold algorithm that basically says add some noise to your threshold, and as you get queries, add noise to the true values of the queries, check whether they're over the noisy threshold, and respond accordingly, that this algorithm is differentially private. What do I owe you? Yeah. Yeah.
It seems to me, so I get the new eyes of fresh for each query, but it seems to me like the noisy way to be, it's somehow, I mean, you said the F I've chosen after.
Yeah.
If you chosen, like after you see the answer for one, for each one, then you can maybe, if you reveal something about maybe, I don't know, don't say formula.
Right, yeah.
The noise.
Yeah, so the adaptivity is sort of a subtle issue in here. And I guess I'm trying to think what's the best response to sort of this concern about adaptivity. So one way to convince yourself that you're okay in terms of adaptivity is to sort of do this proof as we just did it, where you're fixing the news and the Fs. And then to convince yourself that once you've done this, having fixed the news up through L1 and the Fs through L, that you can roll it back one step. And that you can have chosen that F sub L adaptively, given the answers, the previous draws of noise, the previous choices of F, and the answers you've seen so far. And then you can so one way to convince yourself is, and I think for me that's sort of the most sort of pedantic but convincing way to do this, is to roll it back a step and to see, okay, and I still get this same equivalence and with this same sort of e to the epsilon relationship in these probabilities when I'm only fixing up the news up through L minus 2 and the functions up through L minus 1, and I'm conditioning on the subsequent choices of news and L's. And then you can roll it back another step and roll it back another step and roll it back another step and see that you're okay in terms of the adaptivity. But it is a subtle point. Yeah. Other questions about what we're doing here? Okay. So now, what do I owe you? Accuracy, of course. Of course, of course. And because you can't make sense of that privacy proof without knowing what it's going to tell us in terms of accuracy. Because in some sense, something weird happened. We answered K queries, and the K just disappeared. We got, epsilon differential privacy. And the question is, where is that K going to show up? And how is it going to show up? And what we're going to see in this proof that we're about to do is the cool thing is the K is only showing up in a log here. And so in some sense, we're really paying for that one last query where we finally said above. And those queries where we're saying below, we're not paying so significantly in those queries. And that's the sort of cool thing about this approach. Okay, so in order to prove an accuracy theorem, first I guess I need to tell you what I mean by accuracy. So let me do that. So what's the idea here that we want for accuracy? So basically, so we want to say that an algorithm outputting a sequence of answers in response to a sequence of queries is alpha beta accurate if what? So let's say with respect to a particular threshold, if except with probability beta, well, it doesn't halt too early. And also, it says bottom when it's supposed to say bottom and says top when it's supposed to say top. So for all times when it's saying top, actually we're in a situation, so all the times when it says above, we're actually in a situation where we're approximately above threshold. And all the times that it said below, we're in a situation where we're approximately below threshold. Okay? So that's what we mean by accuracy. Every time you said we're below, we're about below. Every time you said above, we're about above, and you didn't just decide to stop answering questions unnecessarily. Okay? Okay, and so before we go and prove our accuracy theorem, let's think a little bit about what can go wrong in terms of accuracy for this algorithm. Where are the places where this algorithm can go awry? So we have a couple of things that can go wrong for us. So first of all, the noisy threshold that we pick could be really, really noisy. And if the noisy threshold were really, really noisy, we'd, halt at the wrong place, we'd say above or below at the wrong place. The other thing that can go wrong is that we can add too much noise to one of those counts such that we say above even though it isn't, or we say below even though it really isn't. Okay? So basically we could get unlucky in having noise that pushes an evaluation of one of these functions sort of over a threshold, and we could get unlucky in having a crazy threshold. And those are the two things that we need to control in order to get our accuracy theorem. Okay, so given sort of those two things that we want to control, let's think about how to show an accuracy theorem. So basically, it would suffice to show that, so let's say that our threshold wasn't too far off, and our noise wasn't too big for all the rounds, right? Because if every time we didn't mess up our thresholds too much when combined with our noise, so we weren't able to deceive ourselves by more than alpha about whether we're above or below threshold, then we'll be accurate with regards to this accuracy notion, right? And we won't stop early. Okay, so in particular, it also suffices that our noisy threshold isn't more than alpha over 2 off, and none of our noises that we add to any of the individual functions are more than alpha over 2 off. Right? And if we hadn't done the annoying thing in how we wrote this algorithm of choosing, slightly different Laplace parameters for the noise on the thresholds versus the noise on the evaluations, then this would be really simple sort of union-bound argument. Oh, sorry, I added a page in the wrong place. Let me add a page in the right place. We just have a sort of slightly more complex union-bound argument. So just remembering, so recall, if we're drawing y according to a plus of b, then the probability that our magnitude of our y exceeds t times b is e to the minus t. So the probability that our noisy threshold exceeds alpha over 2 is, well, going back to look at the algorithm for the moment, what do we do to our thresholds? Our threshold had Laplace 2 over epsilon. So the probability that our noisy threshold exceeds alpha over 2 is just e to the minus epsilon alpha over 4. And the probability that the max over all our rounds of our noise exceeds alpha over 2 is bounded by k times e to the minus epsilon alpha over 8. Okay? And so one sort of coarse way to bound sort of these failure probabilities is to allow the first failure probability to be beta over 2. And that's going to give us an alpha of greater than 4 log 2 over beta over epsilon. And setting the second failure probability to beta over 2 gives us an alpha of at least 8 log 2 over beta plus log k over epsilon. And so together, these two bounds on our alpha give us this theorem that we have here. So let's try to make sense of what this theorem is saying. So we now have this algorithm that says, give me a sequence of queries. I'm just going to say below, 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 below until I get to something that's above. And I'm only going to pay logarithmically in the number of questions you ask me instead of linearly, because I'm not telling you the answers. I'm telling you something that's somehow less informative. And so that's why we're seeing this log k here, which is kind of nice. So let's try to build from this. So we wanted to build something a little bit more sophisticated, so let's try to build on this. So what if we wanted to be able to handle not just one above threshold query and detect that we had one query that fell above our threshold? What if we wanted to do that for multiple above threshold queries? So C of them. This sort of obvious thing to try is, well, let's run this above threshold algorithm C times, and you just restart it every time you hit something that's above threshold. That's, yeah. Oh, sure, yeah, gladly. Yeah, so basically what I did was I had sort of these two kinds of failures, and I said, well, let's make each of them, be wrong by a most alpha over 2. Let's make each of those probabilities of failure happen with probability at most beta. Beta over 2, so that they add up to be beta in total. And then so each of those is going to induce some lower bound on what my alpha is going to be in terms of my epsilon and beta. And then you just need to make sure that both of those alpha bounds hold in order to get your overall guarantee. And so you could split your alphas and betas differently. You could pick slightly different settings of, how to add your Laplace noise, and you get slightly different constants showing up. But this is sort of the basic idea of how you do this. Yeah, questions about what's going on here? Need another minute? Okay, so if we have C of these above threshold queries, we can just restart each time. And then how do we analyze privacy for this C restarted above threshold algorithm? Well, we can use our composition theorems. And we can even use these sophisticated advanced composition theorems that Kobe was talking about. How do we talk about an accuracy guarantee? We can union bound our failure probabilities. So it's actually really straightforward to go from sort of a single above threshold to this C above threshold approach. Okay, and then the next thing that we might want to do is we might want to be able to give not just, hey, you were above threshold, but maybe we want to actually answer the queries that fell above the threshold. How might we do that? Any thoughts? So we have the ability to say below, 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 above, below, 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 above. Yeah, so what would you compose with this algorithm? You would compose an evaluation of those actual functions. So after you raise the, hey, this query was above flag, why not call your Laplace mechanism to actually evaluate that query? And then you can return the values of each of these above threshold queries. So again, to do this next level of the analysis, it's a little bit of annoying work, particularly if you're doing these sort of advanced composition theorems, because they get a little bit messy. But that's sort of the basic idea. And so the type of guarantee that you might want to give, let's just think about what accuracy might mean for us. So if we were doing a numeric sparse thing, so you want to say below, 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 below 27, below, 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 below 35, what does accuracy mean for an algorithm like that? Just informally. What are the things that you would want your algorithm to be doing in order to call it accurate? There are a number of ways it could have messed up, right? Pardon? Okay, yeah, so good. So you're saying when we say below, we should be approximately below. When we say a number, it should be approximately the right number, and we shouldn't stop earlier than we'd planned to stop, in the sense that if we set out to answer C above threshold queries, we shouldn't just arbitrarily stop before that. So it's basically the same types of conditions that we had before, except now we say, if you say below, you should be approximately below. If you say above, you should be giving approximately the right number. Okay? And I don't think I even need to write that. So, but that's the notion of accuracy that you would probably want for an algorithm like this. And then, with sort of basic manipulation, you can do a version of this to get your compositions to provide you with a numeric sparse algorithm that's simultaneously epsilon delta differentially private and gives you this accuracy theorem. And sort of when we write theorems after we've done composition in order to get the theorem, a lot of times we sort of write two versions of the theorem. We write an epsilon 0 version and we write an epsilon delta version. And so here we have, for us, if delta equals 0, here's sort of the basic composition version. And if we have a delta here, then we have this advanced composition version. And so yeah, it's got all these nasty constants in here. It's a little hard to parse. Let's try to make a little bit of sense of what these theorems are really saying. So the first thing that I'd take away from this is that sort of up to constants and this log k that we're seeing in these theorems, this is basically as good as we could have gotten if somebody had told us in advance, here are the C above threshold queries. Answer these queries. So that's pretty cool. So you're seeing this sort of root C, which is the key thing here. You're seeing this sort of C here, which is the key thing here. So basically, we're getting the ability to figure out which are the above threshold queries and answer them almost for free, despite the fact that this is adaptive and we don't know in advance. That's pretty cool. And it's also pretty much as good as we could have gotten if the functions were non-adaptive and we'd use the exponential mechanism to find the above threshold queries. So we'd ask the exponential mechanism, tell me which are the above threshold queries, and then we'd use the Laplace mechanism to answer them. Now we can't do that because we're in an adaptive setting. We don't have them all and the ability to sort of check which are the ones that are above threshold using the exponential mechanism, but we're doing basically as well as we could have done in that non-adaptive setting. So those are the sort of two things that I would take from looking at these bounds is, hey, this is pretty much as good as we could expect. This is pretty cool. Questions about what we've done so far here today? Okay, so this is a tool that we're going to see in John's lecture and also later this week. And so it feels, as we've presented it so far, like it's kind of a limited thing. You know, why on earth would you want to answer only the queries that are above a particular threshold and not the other queries? It sounds really sort of, I just made up a problem and solved it. But what we'll see when we instantiate this and use this as a tool is that in many cases, we'll use this as a tool in situations where we have some sort of candidate way of answering queries as they come in. We already have some guess at what their answers might be. And if our guess is good enough, we just want to go with it, and we don't want to pay for it. But if our guess isn't so good, we'd like to sort of go to the data and pay for that query. And an approach like this is going to let us detect when the answer is close to a guess that we have. So instead of doing above threshold, it's within range, but same sort of idea. And if it's going to let us only pay for the queries where our answers that we already have as candidate answers are not good enough. And so that's sort of the intuition that I'd like you to take as we move to the lectures that build on these ideas. Any other questions, thoughts? All right, let's break. Thanks, guys.